Hello, math fans. I'm Dr. Andy Lovelace. I'm going to talk about quadric surfaces, which is our intro to 3D surfaces that we do in our calculus course. We really don't have to be an expert. There's a lot of interesting things to say about them, but I'm going to try to keep this video and the one that follows it to sort of the basics and the practical and hopefully demystify a little bit. This actually is an extremely easy section in our course, but students view it as a hard section. And so in class, I always dispel this confusion, and I hope to do that in these next two videos here. So briefly, part of the confusion people have is just they don't know their 2D graphs, but even then you're going to be all right. So in 2D, quick review. If I allow, and I'll show you some cool visuals on this video. I will finish by explaining all those, and then I'll follow up with how you can quickly identify them, and then I'll make some other things. So this is what you can get if you allow squares in 2D. So in 2D, quick review, this is what confuses people is as soon as you start writing things in generality, you get all these constants. And so I want to demystify that a little bit. The truth is it doesn't matter if all those are, if some of them are zero, it's maybe, a little different, but it really boils down to just a few cases. What if one of them squared and the other one's not? You actually know that really well. Here's an example of that, y equals x squared. Most students know that really well. You might say it doesn't look exactly like that. You're right, it doesn't. I would have to say d is 0. If d is not 0, it's just going to shift it. I think people don't realize that this doesn't change things very much. It's just a parabola. So this is just a reminder of 2D, because in 3D it's very similar. If one of them is squared, it's a parabola. It turns out it also works if the y was squared, it's a parabola. It's a parabola on its side. So in general, the rule is if one is squared, it's a parabola. Okay. If they're both squared and there's a plus between them, it's a circle, as long as the d isn't negative, in which case it doesn't make sense. So there's a lot of these little caveats, but it's a circle. If you change some of the numbers, these numbers really just rescale things. And I'll talk about that in a second when I show you this visual. The last one the students have the least familiarity with is what if they're both squared and there's a minus between them? It's a hyperbola. And I'd be happy to do more review on hyperbolas. It's just more than we need. The tried and true method when you don't know something is to plug in points. If you plug in a 0 for y, you get a 1 and a minus 1 for x. 1 and a minus 1. And ultimately this looks like this. It's impossible to have x be 0. So I pointed these names all come from the ancient Greek. There was a book called On Conic Sections by an ancient Greek mathematician. And he used these names. They'd already been around for a while. And I'm not an expert. I just was doing some research on this. I remember this picture. I've seen it many times of a hyperbola. These are all called conic sections. If you slice a cone with different planes, this is what you get. So if you've never heard this description, you get circles. If you allow other numbers in here, like a 3, you get an ellipse. It just stretches it a little bit. Turns out the word ellipse means deficient, like it not falling short of these other things. The angle is not enough. Once you make the angle big enough, you get a parabola. And parabola means something like, the direct translation is throwing beside. So it goes around the side of I think the actual terminology has to do with comparing it to the area of a rectangle. So I'm saying a little wrong, but it comes from the Greek. So you get this parabola, and hyperbola is as soon as you go too far. It literally means throwing beyond. So parabola means throwing beside. Hyperbola means throwing beyond. That's why sometimes the word hyperbola, hyperbole, we use as going beyond in some way. The point is, there's really 3 main cases. As long as there's one thing that's squared in 2D, and the other thing is squared to the first power, it's going to be a parabola, hyperbola, or circle. If you tweak those other numbers, so here on the right, I'll make this a little bigger so you can see it, because we'll play around with this just a little bit so you can get a sense. So if I tweak the other numbers, so here's if A is 1, B is 1, and D is 1, the unit circle. If I change A and make it smaller or bigger, you can see it makes an ellipse. It just stretches it. So don't let if there's a different positive number in front of A or B, don't let that throw you off. Now, an interesting thing is if you tweak like the number F, let's see what it does. And I was going to go through and explain this, but I think seeing the picture is enough. It rotates it in some way. It does some shear rotation. So I think we can say, I think in graphics, they would call that some sort of shear movement or rotation, but it still in general is an ellipse. You can see that. So we're not going to go into how to do that. If you change the other number, so let's make it so it's just back to the middle. That one you should already know. These accomplish a shift. You should know this already because you can complete the square in those situations. So that's all that does is it shifts it. It does change the center, it changes the radius, but it affects a few things. So I'm not going into all the details, but that's it. If you change the D, it just makes the radius bigger. I'll make one of the numbers negative. So let's make B -1, just so you can see that hyperbola. There's a hyperbola. That's it. And if you, again, on this one, if you change the other numbers, the F, it rotates it. You've seen one of these hyperbolas before. Y = 1 over X. Cool. All right, that was sort of fun. All right, so now let's go back and look at the 3D. So in 3D, I say that partially to demystify this. This looks extremely messy. What if we allow squares and we allow every possible combination? These things, it ended up being the same thing. These are some sort of shear / rotation thing. So we don't usually study that because we say, okay, I was going to do a video on actually showing the transformation. I realized that's going to take a lot of work for me to clearly explain all that, and it's not essential for the course. These ones do this same, moving the center. So these are more like a translate. Again, I'm not being fully complete, but those pieces are not essential to the general analysis of the types of shapes. The shapes are equivalent, but turned in some way. Okay, we say there's an affine transformation. So anyways, it really boils down to studying this and possibly what if some of them aren't squared, just like we did in 2D. And it turns out there's 3 flavors. This is how I explain it. There's paraboloids. There's 2 flavors of that. There's hyperboloids, and there's 3 flavors of those. And there's spheres or ellipsoids. So it's very similar. I explain this in a little different way than a lot of people do because I explain it in how it logically makes sense to me. So in this situation, you can see, and I'll talk more about how I actually name these. I don't memorize these names. I have a way I can remember all of these at any time in the future. And I will explain how I do that in the next video. So I don't memorize a table. I don't put a table on my note sheet. I know the names. And I'll explain why. But here you can see one of them is not squared, but there's this thing of a plus or a minus. That's why there's 2 flavors. Here you see all 3 are squared, but there's a minus. And it turns out there's 3 flavors of those, depending on whether this side is positive, 0, or negative. And then the last thing is an ellipsoid. So just to show a quick visual, and I'll share these Desmos graphs, but here's a visual in 3D. We'll play the same general game of transformation just to sort of say what I'm talking about, that you can transform these as you like. So there's when A is 1, B is 1, and C is 1, and D is 1, and everything else is 0. So if I change any of the A, B, or C a little bit, it will make it an ellipsoid, stretches it a little bit out of shape. That's all that does, changing A, B, and C. If you change U, V, or W, the numbers next to X, Y, and Z, you're going to shift it over a little bit and change the size. That's that translation. So the interesting ones are the F, G, and the H in terms of they do some interesting things to it. So let's tweak a couple numbers. Let's make it so that, well, for now, let's make the C 0. Apologies. Can't quite hit it on the head. I'm going to type it in. So we'll make the C 0, and then we'll make it so there is a Z. So we'll make the W 1. So there's an example of a paraboloid. You can see that. One of them, two of them are squared, and one of them is not. Now we're going to do some of this shear, change the F. So if I change the F or the G, it tilts it. It's pretty cool. I've never really played around with that. So it's still the same shape. The point of me showing you that is these F, G, H, U, V, and W don't really fundamentally change the shapes we need to study. They're really interesting. And if you're going to rotate in some way, you get all sorts of things here. So if you want to play around with these numbers and what they do. But the point of me making this so that you can play around with it is to see that the same general shapes are still there. So that's kind of fun. So make some fun shapes with that. Play around with it. Whoa, what's that one? Let's rotate it a little bit. Let's play around with these numbers. Now, if you really want to rotate it, the best way is to multiply it with a matrix. That's why I realized it was going to be too long. But there you go. Those are the quadric surfaces. So in the next video, I'll talk about naming. It's actually really easy to name them. But the point is, in 2D, we have parabolas, hyperbolas, and ellipses, or circles. And in 3D, we have paraboloids, hyperboloids, and spheres. There is one kind of degenerate hyperboloid that we don't call a hyperboloid. In fact, I sort of disagree with these namings. I wish they were just all called hyperboloids. But one of them has a special name, which is the cone or the double cone. One of them is called a hyperboloid of 1 sheet. One of them is called a hyperboloid of 2 sheets. Again, I'll explain that. I will, after I talk about the naming conventions, I'll make a video on paraboloids just to go deeper than I've ever done before, because there's a lot of cool things where these are used. And then I'll make a video on hyperboloids and go deeper on that as well. Those are not essential for the course, but will be more fun. All right, thanks for listening.